Got it. I'll be there. Oh, there's some possibility I'll be there out of places. My daily routine, like I told her how to like oh, I really this good. Why don't you? Yeah, this is what I have planned. Okay. Well, I think okay, this is like I know it's faster than we did. Yeah. We're pretty cool. I was class. Probably not. I'm not taking it. Really? Yeah. No, I'm not taking it. If it happens, the next is the college. Taking it. Oh, this is what if I dodge it? I mean, I could just take 4 goals instead. I could just take 4 goals instead, like databases, but I don't care about 4 goals. 434 the content is probably more interesting. I got to like it's felt like full brain truth. That's what I knew that the burnout was setting in. Heavy. Like this world's heaviest burnout. Yeah. Oh, that's not too bad. I'll do it later on everything. It is. Yeah. I have friends from all around October 27th or October 30th. Yeah. The brain. Oh, you have a new one. That's cool. Oh, this is I need to take. Oh my god. I think guys who registered the communities because they're nerds and they accommodations. Oh wait, what? No, it's better to be. This might be small. Yeah, this is small. That's the thing. You're right. But I just signed up earlier. Yeah. Yeah. So I'm definitely this because it's a Monday, Wednesday, and I need that because then I can hang out with friends or something. Then that means I just gotta have a state where that's what's available. It's just like this. These aren't really like my work these. This is good. I'll enjoy this class, but I won't enjoy it. Oh god. Are you taking any practicals for your goal? I'll avoid the not the instructions are clear. Yeah, taking this one and Probably taking this one, taking the capstone. Probably going to the taking.
Even if I'm right now.
Yeah. My energy uses computer for architecture. It's because it sounds cool. Yeah, how much you? You have an X-Ball? Dude, I'll take it on. Take it now. I'll take it. With this spring.
I can take it now, to be honest.
Might be some pump that it sounds like it's 2:30 or more. Versus pumps, steps on design, basic processor implementation and pipeline.
Yeah, I can have one thing I can take this. You're on.
It is right after 2:30 on.
Yeah.
No.
I consider it.
After hearing this, what do you know or what you use for? Sounds like something that popular and also sounds like something that quantity. I'm trying to find a way to use out my last semester. It's my burnout is really right now. And now it's, yeah, but I have to take something like this.
No. 10%.
I'm trying to hyper-condense my days.
Oh, yeah. Can't do music for kids.
Can't do Monday, Tuesday, Wednesday,
Actually, no, I have my kids not really. So if you can find US 324, we get US 324 USB yeah. 324 and more importantly, it is internet coverage already if you have less to over it. I'm not even kidding. Because kind of class is this kind of help Reddit. It's not offered. Yeah. It's offered like I don't think it was genuinely one of the most different things when you have to take it. Like it talks about stuff like not getting the time. It's 224. I don't know, it might not be offered.
It's 70 or she said it's
374. It should be. US.
Wait, we can go.
Times.
Yeah. Last fall.
Elevate, right? The entire class is held up, right?
I think this might be one.
Yeah.
Like for one, yeah.
Oh, really?
I know guys are taking questions right now, that like, if you've got people like Russian, like 5 minutes in the semester. That's great. But like,
Think with that if I don't take to school right away, I'm just back. As the president. Yeah, maybe my wife had changed, who knows?
Really, I'll collect your data. Oh, yeah. Drop somewhere.
Yeah. It does.
It's better to work.
I'm
I guess what it's saying should be doing this.
Was it 416?
Yeah, I think I've seen you there.
Yeah.
That test was like.
Yeah, I was like, I definitely did great. Let's see if I did okay.
So much in that area of the answers. Like I hate that test.
Especially when you're not familiar with like someone.
I like them.
Now you guys go off with me, I was like, oh, it's like.
So you go
Long route. Then all of a sudden, it's not a little bit, like, not as early as that.
Yeah, it's really
Good time to get off. Oh, yeah.
It's a pretty. So I, I had to walk. Sorry.
I was reading that on Friday.
Okay. So we will get started. Next class, we don't have a class on Tuesday because of fall break. I assume you all have plans to get out of the town. And then Thursday we'll be back. And then at some point of time, after you come back from fall break, there will be a bit of, I don't really care about exams, but I should give you some exams, right? Otherwise you would not feel good. So there is, I can do take home or in class. Okay. How many of you have ever done take home exams? Okay. Not in at ASU, right? Okay. Okay. So basically I'm going to ask, I guess we'll take a poll just to get a pulse. I mean, I'll still decide what I'm going to do and I'll let you know. So the in class would be, that means during the class, okay? It would likely be, more likely than not, it'll be the week after you come back, because when you come back, you just have Thursday, okay? Take home means that I'll just give you, everything is done outside the class and on your time, and then you submit, okay? Anybody has any questions on this stuff? So how many people are for in-class exam? How many for take home? How many for no exams? Okay, so we'll do something like, I guess more likely something I can take home. But again, as I said, please remember, this is an honors class. If you are caught cheating, I will make sure that you'll get out of the university. You understand what I'm saying? Please don't do it. I mean, I'm pretty bad even for non-honor students, but I trust you when you're honor students. And that's why I don't think we normally do take home for the midterm. I've done take home for the final because by that time I have a sense of the class. But I'm giving you the break, hopefully, assuming that we're doing it that way. Yeah, go ahead.
What will the format for take home be like?
It'll be a take home.
Yeah, what do you mean, like, what will we be allowed to access? And
I'll let you know all that stuff. I mean, basically, take home basically means that you can read anything that you have except trawl directly for answers on the web. So you can read your notes, you can read the textbook, you can look at the videos of the class and so on and so forth. You're not allowed to trawl specifically for, again, remember we are living in the time of GPT-3, right? So you can essentially take the entire question, put it on Google, Google will say this is the answer. And you just copy it, but I don't need you to do that. Okay. Yeah, but we'll say all that if we do take something. Any other questions? Yeah.
If it's a take home exam, does that mean that we have to do it individually too?
Yeah, exams are individual.
Okay.
Exams are individual. Actually, nobody specifically asked me, but I think for the exams, you are allowed to ask questions to me and basically the instructors, but not to other students. Homework, you can ask questions to other students too. It's just that, essentially you do your own work separately. Okay, so homework you learn. As long as you don't copy each other's answers, that's fine in homework. For the exam, you're just basically saying what you understood. And it's fine if you ask questions on the piazza. We will decide whether to answer or not. Yes, go ahead.
what would the time frame be for the exam?
That I have to figure out. It depends. It may be some I haven't figured out. Okay, any other questions? Okay, but please don't think that take home means you don't need to study until there would be ways in which you would get delayed if you are not keeping track of information and you just try to study just after the exam. It's not going to be worth it for you. Okay, we'll do it more likely than that way, but I'll give you more heads up on this. Okay, any questions before we get started? Okay, so today we're going to continue where we left off, sort of. So basically review Perceptron update rule once more and talk about the multi-class perceptrons, where you talk about basically introduce cross-entropy laws and also talk about softmax layers. And it turns out softmax is essentially a generalization of sigmoid function. And that answers somebody's question last class as to how do you make sure that something becomes a probability distribution. Softmax layer makes sure that the inputs are essentially, you take each input divided by the all other inputs, except it also does exponentiation of each input divided by the exponentiation of all the other inputs. And then that way gives you out what will essentially be a probability distribution. We'll look at that in a minute, okay? Then we'll talk about expressiveness of perceptrons, which should not be surprising because perceptrons for this class should not be surprising. We went from linear sum of, we basically, when we started the reinforcement learning part, we looked for linear sum of features, weighted sum of features, okay? And then I said that corresponds to linear perceptron, okay? Just by putting the G at the end, I noticed we talked about perceptrons with no threshold, but we also talked about perceptron with threshold. If it is a single layer and you just have a threshold function, it doesn't change the linearity of the perceptron. What it changes is, instead of it being perceptron being used for regression, it gets used for classification. You understand what I'm saying? So, and in fact, originally when perceptrons came along, people were using it more for classification than for regression. Even though both are equally important problems, as I said, regression essentially is giving, given the values of a function, real valued function, trying to guess the rest of the values of the function. Okay, classification is given the categorical functions values. That means a real input but categorical output. Guess the categorical output for new inputs. That's the only difference between regression and classification. Okay. The thing is that originally people were a lot more interested in the classification stuff. When Rosenblatt came along with perceptrons, and then they weren't particularly, I think he was aware of it, but essentially it was one of these things, as we'll talk about. Basically, the fact that perceptrons are linear, which should not be surprised at all. You're not surprised at all. But that sort of historically became the reason why people stopped doing neural networks for a whole bunch of time, strangely. Okay, one of the other things that you'll notice is science is a human activity. There is no rationality in the way science is pursued. Science itself is rational. But the way science is pursued is not rational because we do it. We are irrational people. All sorts of random things, like in history of science. How many of you, for example, know that calculus at the time Newton and Leibniz invented calculus at the same time, more or less. Leibniz had the more nicer notation of this d by dx notation. For example, Newton was actually looking at it in this dot notation. He used to call them fluxions. And this kind of led to some sort of a crazy rivalry between UK and Germany. And it's well known that Newton, who looks like a nice saintly guy, he's vindictive as heck. So there was a time he wanted to make sure that Leibniz doesn't get any credit. So basically, Leibniz tried to be a nice guy, and he said, okay, here is this stuff. Why don't we talk about Newton, Leibniz precedents? Who did calculus first? So Newton was the head of Royal Society at that time. He appointed a committee, hand-picked committee, told them what to write in the report. Didn't believe that they'll write it anyway. So he threw away the report, wrote it himself. And then said, Newton invented everything, Leibniz is a bozo. And the sad part of this is for the longest time, UK mathematicians would not use Leibniz notation. So it's been said that for about 100 years, UK went into like a deep funk because they were trying to get by with a different formulation of calculus. Okay, how rational is that stuff? Like I said, science is never rational. I mean, pursuance of science is not rational. Science itself can be rational, but pursuance of science is not rational. So similarly, for strange reasons, people just stop, looking at neural networks just because, oh my God, they're linear just as we thought they were. And so that was enough. Right? It turns out that you can increase the expressiveness. In fact, how many of you have seen that fun in the TensorFlow sandbox thing? Okay, the rest of you should definitely make time to see it. Those of you who did it already are in kind of good shape in figuring out what we're talking about. But essentially, what we showed in that sandbox thing is that you can increase expressiveness either by essentially blowing up the inputs into more dimensions and then doing a linear summation of that, or just increasing the number of layers, even by one layer. And it turns out actually there's not that much difference. Suppose this is the inputs, right? To blow it up to a bigger number, in essence, the new dimensions would be connected to the old dimensions. Those of you who have seen that examples in Sandbox, you'll, for example, start seeing the new dimensions will be not only x1, x2, but x1 square, x2 square, x1, x2, etc. So that means some features might be dependent on more than one initial feature. So you can actually say that these guys, like for example, if this is, let's say, x1, x2, it's basically taking lines from both x1 and x2 and multiplying them. So then these features are then fed to a perceptron unit, which will only do linear weighting of these features. So either you can think of linear weighting of nonlinear features derived from the input, right? Or multiple layers where the input features are nonlinearly transformed into interior features. Either which way is essentially theoretically equivalent. Okay. And so one of the interesting things there basically, as I said, I mentioned last class and it will come again today, is in those cases when we are actually stacking up layers, it's very important that the threshold function be nonlinear. The threshold function is not nonlinear, then just stacking a whole bunch of linear layers will get you another linear function. Do you see what I'm saying? Okay, so that winds up being very important. So we could do either this or multi-layer networks, and then we'll talk about training of MNNs. And it turns out training of MNNs is one more place where people got stuck for no good reason whatsoever. If you understood essentially what you understand now, what we understand now, is that basically we're just applying chain rule to compute the differential and then use that to do gradient descent. You could do that if it's only 1 layer or 2 layer or 15-layer network. It kind of becomes pretty darn painful if it is multi-layer network in terms of keeping track of all the W, JK, WKM, etc., which we'll see. We will, for example, show the generalization of Perceptron for 2 layers. I'll just show you how the derivation looks like once in your life. And then we'll say, thank goodness we are in computer science. We don't need to ever do it by hand. It turns out that the derivatives can be computed in the backward pass, essentially in a programmatic form. So that's like the great contribution of computer science to this part, essentially. Okay, so in a weird way, once you understand that what is getting done is this chain rule, you don't have to actually do it yourself. Last class we did it for Perceptron. Today I'll show you for 2-layer one once, so it looks actually quite imposing. But then I'll say, in fact, nowadays you have 250-layer ones. And if you imagine sitting down and writing the update rule for every possible weight by hand, you'll never get done anyway. It turns out that there's this beautiful way in which you go forward to compute the outputs, you go backward to send the derivatives back. And it just works. And all you need to know is understand how pieces of derivatives are getting sent, and we'll show you that. That's basically backpropagation. That's the overall picture, of some of which we'll get to, the rest of which we'll get to next week. Okay. Any questions before I go forward? Okay. So very quick review. So this one is like a huge summary of all the things that I discussed before I even shifted from the first slide last class. I just added that. We talked about, these are all review slides. We talked about linear regression in terms of perceptrons. Okay, I'm going back. Okay, and then we talked about perceptrons and the brain connection. We talked about regression versus classification. I'm just trying to show you these things, right? And then we talked about, and we'll again talk today, we talked about the fact that perceptrons can be used for binary class classification. First of all, they can be used for regression or classification. And if you're using it for classification, you can use it for either binary class, in which case, if this thing says 1, that means class 1. If it says 0, it must be class 2, or whatever, vice versa. You can also do perceptrons for multi-class classification, which is this. And this is where, in essence, I told you that the output is probably, you may want to view the output itself as a probability distribution. And then I'll try to explain to you today that this particular set of nodes. So here, normally, the G function is a sigmoid function. For this, for the multinomial perceptron, the G function is best seen as a softmax function. I'll show you in a minute. And the softmax just automatically normalizes the inputs into a distribution. It could have just done it by input 1 by the sum of all inputs, that itself would work. but it actually does e power input 1 by the sum of e power each of the inputs. And the exponentiation, what it does is minor differences in the inputs get accentuated in terms of the probabilities. So this is why actually the word max comes in. It's a soft way of taking maximum. If you have k values, you take the maximum of those. You may want to do maximum once in a while. That's not differentiable. Max is not differentiable, but softmax essentially gets you that. It essentially, the thing that is a little bigger than everybody else becomes much bigger. So the probability of that becomes much higher. And so it's called soft version of max, softmax. Okay, we'll look at that in a minute. Okay. And then we looked at the perceptron gradient calculations. So the one thing that was confusing last class is towards the end when I was doing this is what I was really showing is the error calculation for one example at a time. So there was a question as to what happens if you have multiple examples at the same time, which you're doing batch. And then all that changes essentially, and that I sent a long mail also, all that changes essentially is that the error now is it's a summation of errors for each of the examples. Notice that each of the examples have different input features and different outputs, right? But all of them share the same weights. The weights are the same. Okay, so in essence, the gradient now will have contribution from each of the examples, and the contribution of the gradient will essentially look like as if it is a single example. Each example winds up contributing the same amount as that one example that we did. And so all these are added up, and then there is a bigger gradient and you take a bigger step. Except this summation is, of course, sign sensitive. So some gradients may be positive, some might be negative. You are adding them up. So in fact, the vector, remember, first of all, other thing that you have to remember is gradient is a vector. Gradient is a vector. In k dimensions, gradient is a k-dimensional vector which shows the direction you have to travel. And in essence, weight itself is a vector. You subtract alpha times the gradient from this. So you do item-wise subtraction or addition, depending on whether you're doing gradient ascent or gradient descent. Okay, so that's basically the only difference between batch versus online. Then I actually sent this longer one, which does it. Basically, the main thing that you need to keep track of is each example. There is more than one example, so you have to keep track of each of the examples, E1 to EM. And then each of them have their input features, and there's an expected output, and what the network is saying is the output, and you have to take the error. The nice thing is all the examples are connected. It's not that examples will have different weights. All the examples use the same weights, which is the part we were talking a lot about at the time of RL. Because if you're changing the weights to make one particular state come closer to its value, then in effect you're changing everybody's value, because the weights change, the values change. Question? Okay, so in essence, what happens when you have batch versus online is, in the case of online, essentially each example's error is subtracted from the weight vector, and that will be a new weight vector now. With respect to that, you use a second example, and then there'll be a new one extra vector. Whereas in the batch, you have one set of weights, current set of weights. You look at all the examples, take all their gradients, add them up. You will get like a probably more robust vector. It's not necessary that the vector will be longer because it can cancel out. Okay. And the robust vector, so original weights minus alpha times these robust gradient vectors would be your next step. So in effect, batch can take in theoretically fewer steps, but it turns out that actually, as I said last time, the stochastic gradient winds up actually doing better. And I asked this in the write-up that does anybody see the connection between batch doing worse than online and prioritized sweeping versus synchronized value iteration? Remember the synchronous value iteration, the way that we thought of value iteration was everybody's value at 0 is computed. Then V1 full of them, then V2, then V3, then V4. This is how we computed, lockstep. But then I said, actually, in fact, when you are looking at VK, you always looked at values from VK minus 1 to update VK. But I said, you don't need to do that. You can actually just, update in any order. And you don't even have to wait for the previous, you don't have, if you look at the kth iteration for this state, and this other state already is at the kth iteration, you can take the current kth iteration value rather than its k minus 1th iteration value. Because it actually will be closer to its real value. That's the same thing that's happening in online, because if you do a few online, every time you do a change to the weight vector, you now have a new set of weight vectors with respect to which you're again looking at the next example. That's a kind of intuition. It's not a mathematical proof. That's an intuition as to why looking at, even though all the examples are in front of you, looking at them one at a time is actually doing better. Okay, yeah.
The output of each Perceptron is the value of the whatever value you derive from the given features and weights, or is that like an answer that it's giving? It's like when you're doing all these calculations.
No, what we are changing is W's. All these calculations are changing the W's of the Perceptron. Okay, so see. So all these calculations are changing the weights here. At the end of which you will have a Perceptron with its best weights. When a new example comes, you plug this new example, I1 to IK. You multiply I1 to IK by W1 to WK. So you basically take I dot W. And then if there is a threshold function, you take G of I dot W. That will be the output for that new example.
It's like how we find an optimal policy in MDPs, except in this case,
this is the optimal weights vector. You're finding the optimal weight vector. Once the weight vector is found, then the new examples just basically get processed with respect to that weight vector. Any other questions? These things, hopefully over the fall break, it sinks in more. And, basically these things are going to be layered. Layered literally as well as figuratively. We have multiple layer stuff, but we're also going to go very quickly into networks of crazy configurations that we don't need to worry about how to do the backpropagation. Again, remember that my best example is you never really do differentiation by the first principles, which is limit h tends to 0 fx plus h minus fx by h. But that's the theory. If anything starts falling apart, the way you check why it is falling apart is going back to the first principles. But if you ever really computed differential derivatives all the time by taking the limits that way, you will never get done. In fact, I think there's a quote that I used last time in the beginning of this thing that Alfred North Whitehead said, civilization advances by doing the number of things that we can do without thinking. You see what I'm saying? It's like huge number of steps will become one macro. So then it basically becomes like a building block for something else. Okay. Okay. That's that. And then I mentioned towards the end of last class that gradient descent basically always winds up having, something like weights are being changed by weights minus alpha times the error with respect to that weight. I mean, the derivative of the error with respect to that weight. Okay. And this derivative is computed, the partial derivative of the error with respect to the weight is computed using chain rule. Okay, so in the normal single layer thing, jumping ahead in the normal single layer thing, right? This, let's say, is Wi, and then it was multiplied by II, and then it was added up with all the other guys. So sigma of II Wi, and then you applied a G function to it, and then the output came. The error is with respect to the output. So when you're taking the derivative or the differential of the error with respect to Wi, you need to chain through G to get to Wi. That's what we did. Chain through G to get Wi. That's where we had this G dash business, if you remember. Right? You already did chaining. So jumping the gun a bit, imagine I actually has II here, and then there is a bunch of I1, II, IJ, IK, and these all got connected to, you got OI, which then went to WI and then went out. Now I want to actually decide this weight, WJ, let's call it. How to change this weight? Again, this weight needs to be changed by taking the error here. So I need to take dou error by dou WJ. So notice that if I change these weights, the error will change here. And what you're trying to do is how much to change this weight k layers behind. Right? But from the chain rule perspective, this is the same question as how much should I change Wi, given that Wi is actually going through G. So you chain through G. Similarly, to get dou E by dou Wj, you will essentially chain through G, Wi, another G here, and then finally you get to the last weight. This is what chain rule is, and this is what basically works. What is surprising is it took forever for people to believe that it works. Do you understand what I'm saying? So this picture I'll show you in the 2-layer case. Actually, let me show you just to come back to this. Yeah, there you go. Doesn't this look good? This is the kind of thing that you signed up for. You said, what the heck am I doing in a computer science class with all these many partial derivatives? So in essence, we'll get to here, but essentially I have output, which is coming from these. This is the input layer. The inputs are connected to the middle nodes, which are then connected to the output node. This is your multi-layer network. I'll get to it again in steps, but you kind of know where I'm going. And what I'm trying to do is compute dou E, the error, with respect to the JIs, the weights here. That's what I did here. And with respect to the WKJs, which are the weights here. And when you are computing the weights with respect to WKJ, notice that writing the WIJI, you only need to chain through G to get to WJI. To get to KJ, you need to chain through G, WJI, one more G, then you'll get to WKJ. So notice that in fact, in trying to compute this, eventually you start asking in terms of, so when you're trying to compute d by dou WKJ, with respect to the derivative with respect to WKJ, you were eventually, Yeah. Yeah, so you wound up starting with the derivative from error, and then you wound up going to do A by dou WKG. I'll get to this here again. But basically, this is these layers of chaining you get through the weights. And thankfully, we don't need to do this. That's what backpropagation, auto backpropagation does for you step by step without you knowing it. Okay, we'll get to that in a minute. Go back to where we have. Okay, so this is the gradient, and it's important to realize that we're changing all weights simultaneously. In fact, it's best to think of the update as a vector equation. Weight vectors are being changed with the gradient. Gradient itself is a vector. Okay, and by the way, gradient is written this way. That's the notation. Vector gradient. Okay. So this is how we are in essence deciding the direction in which to move the entire weight vector. And as I said, the difference between online versus a batch is that the total gradient is computed in the batch. You know, we're adding a gradient from all the vectors, from all the examples. Okay. So the other thing that we want to talk about is we've been looking at loss function mostly as the squared loss function, square loss function. But now that you kind of understand, basically all is required to do is derivatives, I mean differentiation over, as I said, actually this differential depends on the loss function form, the threshold function form, and the input values that actually are coming in. And if you change the loss function, all you need to change is just the derivative for that loss function. X squared derivative is 2x. Some other function, then you just take the derivative. Now, what is a loss function is essentially problem specific. So you can decide what is it that you're trying to minimize. How do you define error? Okay, so the simplest question would be the minimum thing, that is, for example, what we said was we essentially will look at, given a set of examples, we want to aggregate the error function. We're basically taking, let's see, the simplest loss function is the quadratic loss function. That's the one we are looking at till now. Notice that if it is, for example, a classification task, then all errors are counted equally weighted. All errors are counted equally weighted. You may want to say that some errors are more problematic than other kinds of errors. Right? For example, in the classification, we can talk about true positives, false positives, true negatives, false negatives. Suppose it's just a binary class. So I'm trying to figure out which of you is a criminal. I'm trying to decide, classify you into criminal, non-criminal. If I say a particular person is a criminal who actually is a criminal, then that's a true positive. If I say somebody is a criminal and they're not a criminal, that's a false positive. If I say somebody is not a criminal and they're actually a criminal, that will be a false negative, right? And similarly, if I say somebody is not a criminal and they're not a criminal, that's a true negative. We know that the errors come from false positives and false negatives. True positives, true negatives are basically good because you correctly classified them. But should we assume that false positives and false negatives are equally costly in terms of errors? Most machine learning algorithms just assume that all the errors are equally costly, and they just upfront that's what they'll try to minimize. So they're trying to minimize the error on the whole. So I can get, let's say, on 1,000 examples, I can get, let's say, 10 errors on the average, and those 10 errors can be, all of them are false positive errors, or 5 false positives and 5 false negatives, are all false negative errors. Do you care? It turns out if you just think all errors are created equal, then you don't care. But you can imagine already, because of the example I gave you, in this example of criminality, which errors are worrisome, more worrisome versus less worrisome? Do you understand what I'm saying? I mean, do you care if I basically am trying to check your criminality by state of the art neural network? Do you think that the false positives should be considered equal to false negatives, or should one be considered much egregious error? What? False positives, especially if you are one of the false positives, you don't like it one bit. What do you think Joe Arpaio says? False negatives. Jail them all. That's it. Everybody will be in the jail. Nobody will be outside on the roads. You'll be fine. So my point is, I'm not necessarily deciding whose values I'm endorsing. Maybe I'm a closet Joe Arpaio, voter. When he gets out of jail, I might vote for him too. Okay. But the important point is that depending on the domain, depending on what it is that you're trying to optimize, you might wind up having a different error. Okay, where essentially there's higher weights for some kind of errors and lower weights for other kinds of errors. You see that? It's called cost-based learning, and then that just changes the weight function, that error function. The other type, so you could talk about cost-based learning. The other type is, again, if you don't differentiate between classes, but you differentiate between whether you think of this as the value of the function, or are you thinking of this as a probability of the class, which I mentioned last time, that if you are a classifier and you have a multi-class classification problem, then what you are outputting, maybe you want to see what the network is outputting, in this case, as the probability vector, as to whether the input is class 1 with this probability, class 2 with this probability, class k with this probability. Okay, to be able to do that, first we need to convert what this guy is saying into a probability distribution. Okay, for that, it turns out we can use softmax output layer, as I mentioned earlier. What is a softmax output layer? For, let's say, for the ith class, right? What I'm going to do essentially, so basically whatever is coming into this, remember, this node will get some weighted sum of inputs, right? W, R, J, I, the I1 to IK here. This needs to be thresholded. Previously, we were just assuming the threshold is a sigmoid function. Here, I will actually say, depending on the class, for each class, the function is e power ik by sum of e power ik, e power I. That means essentially, I will take all these weighted sums, exponentiate them, add them up, put them in the denominator, and this guy will essentially take e power ik by the sum of the exponentials in the denominator. If you do it this way, what comes out will be a probability distribution. Okay. Now, there are multiple other ways of doing probability distribution. This is one way. And as I said, this can be thought of essentially as really what you want to do is, since the class that you are, if you put an input, imagine that for any input, it will be one of the, okay, this is like IN, I guess. It will be one of the k classes. It will belong to exactly one of the k classes. There is no fractional membership. Each input vector corresponds to one of the k classes. If so, really, what should happen is one of these units should be 1.0, all other units should be 0.0. Right now, these units will all be numbers between 0 and 1 such that they add up to 1. Except by taking the exponentiation, the bigger ones are likely to be considerably bigger than the smaller ones. Any small changes in the weighted inputs would be accentuated because you're taking exponential, which is basically what makes it look like a max. You see what I'm saying? So imagine like one of the weights is, for this guy, you're getting 10, and everybody else, you're getting 1, 1, 1. Right? All of a sudden, you are now saying e power 10 by e power 10 plus e plus e plus e plus e. That would make this guy's probability much closer to 1 than if you just did it as 10 by 10 plus 1 plus 1 plus 1. Yes.
Does this work for all bases or just for E?
People use exponent e because it has all these beautiful mathematical properties. That's it.
Or could you use other values like 2?
Yeah, of course. Yeah. I mean, then basically, you know that, 2 power x is not, differential of e power x is e power x. Differential of 2 power x is a little more complicated. You can do it. It's not basically, since it doesn't really matter, so people just use exponential mostly. But of course, it works. Any other questions? Okay, so that's the softmax output layer. I'm sorry, go back. So if I do have the softmax layer, then I'm getting outside here a probability distribution. And since I know that for each input, I know the true class, so that probability distribution will be some 1 in one place and zeros in every other place. So I have to compare two probability distributions and sort of say that when the distributions are different from each other too much, then there's a higher error. Otherwise, there's lower error. I mean, the best case is if in fact the input example corresponds to class 15 and the softmax layer outputs something which has like very small numbers all the way for all the classes except for class 15, where it is close to 0.99999. Then that basically that particular column is very close to 0.0001 0.0000. Right? So you need to kind of define a distance between probability distributions, which you guys have not thought about before. Any of you actually thought of distances for probability distributions? It turns out that the way you normally talk about distance between probability distributions is KL divergence. And what we are calling here, what we're calling cross-entropy, is derived from KL divergence. And what basically it says is, if it's like, let me show you this slide, it's the same. So this is the notation. Y is the true class indicator. Y will be 1 for the actual class and 0 for all the other classes for that example. Okay. And P is the actual predicted probability according to this network. Then cross-entropy loss is basically defined this way: y log B plus 1 minus y log 1 minus B, the whole thing negative. In particular, this really can be thought of expected value where the, let's not talk about it right now. Okay, so that's your class entropy for two class problem. For you have K classes, then it's basically sum over all the classes. The expectation is that y will be 1 only for one class and 0 for all the other classes. But really, cross entropy is defined for any pair of arbitrary probability distributions. If y is not 0 for some, it's fine still. If it's an actual distribution, it will still work. Okay. So if you then write it in terms of cross entropy loss, then you need to do the derivative of these logs, which is okay. We know how to do derivative of logs. You see what I'm saying? Remember that this P, the probability will be in terms of weighted sum, weighted sum of inputs, if it's a single layer perceptron. So it's a log of sigma Wi Ii. That will be 1 over the whole thing, and then chain rule on just the sum. I'm not showing the derivation here, but essentially, because I'm not going to show most of the, we're going to give up on actually trying to derive the derivatives anymore and just depend on the back propagation to do it for us after a while. But the point is, it is important to understand why this kind of an error makes sense. Why do you need different kinds of errors? So there is the square error, there's a cost-based error, which is basically gives different weights to different errors. There's also this cross entropy. If in fact you have perceptrons with binary class perceptrons with sigmoid threshold, it turns out that actually, as I said, the softmax is a generalization of sigmoid. It's a little tricky thing to show, but essentially it's a generalization of sigmoid. That means for the case of 2 dimensions, softmax becomes sigmoid. 2-class problem, so because softmax is different for k classes. For 2 classes, softmax becomes sigmoid. Okay. Now, if you have 2-class problem and you are anyway using sigmoid perceptron, which is what we were doing last class when we were deriving the error, the gradient, except we used error function as the squared error. If we used this error, the cross entropy error, then you would have gotten a particular algorithm that's quite famous called logistic regression. In statistics, if you take any statistics courses, by the way, I forgot to show this, but everything we are doing, statistics people care about the same problem. So in statistics, one of the first very powerful techniques people talk about for classification is this thing called logistic regression. And its regression word makes it look as if you are actually doing regression, but logistic regression is a classification problem. Okay, with the error function being the cross entropy loss, and the threshold being the sigmoid. And it's a perceptron. You see how many things you can change for the perceptrons without increasing the layers. You can have an entire cottage industry, which is basically what Rosenblatt was having at his time. You get interesting behaviors by changing the error function, changing the thresholds, etc. But you'll never really be able to get full expressiveness, and that's basically the point I want to make right now, that can perceptrons learn all functions? Well, obviously, again, this should not be surprising to you. We basically came to perceptrons as linear sum of features. So you know that it's basically computing a line from a regression perspective. From a classification perspective, instead of basically, so if you have, in terms of, if you have a bunch of points, perceptron will try to find the best fit line through those points. From the classification perspective, the question to ask is if it's a binary classification, there are a bunch of negatives and positives, that means class 1 and class 2. Perceptron essentially tries to find a line such that one side of the line is all negative, other side of the line is all positive. So it separates the classes. And the class separator is a line in 2 dimensions. So it becomes a plane in 3 dimensions. It becomes a hyperplane in k dimensions. So perceptron is always trying to either approximate a bunch of points by a line, or find a hyperplane that separates classes. Right? Hyperplane that separates classes. Okay. Now the question, of course, is, this was kind of interesting for people at that time, presumably, because with all these variations of perceptrons, you can change the error function, you can change G value, you can change all sorts of things. You can get a bit of a reasonable amount of performance from perceptrons. In fact, linear classifiers have ruled the world for quite a long time, and they still rule the world now. So in fact, I forgot to show this here, but back in 2017, which was like less than 4 years back, Kaggle, you guys know Kaggle, some of you have heard of Kaggle. Kaggle looked at what are the winners using as their go-to learning algorithm. Most of them were using logistic regression. But they won, which means actually logistic regression works quite well in many, many cases. Much fewer people, in the Kaggle competition, remember Kaggle is not just about image recognition. It can be any arbitrary machine learning-ish problem. And it turns out logistic regression is actually an extremely useful technique. It works quite a bit. But the question is, will it work like all the time? You know that it won't, but basically these guys, Minsky and Papert, looked at Boolean functions, which is like the simplest form of functions, and then tried to show that perceptron doesn't even learn all Boolean functions. So in the case of Boolean functions, basically it's like I1 and I2. So I1 and I2 will be positive when I1 as well as I2 are 1, and then 0 every otherwise. It's a Boolean algebra. And would be 1 if both inputs are 1, and 0 if any of them are 0. And then similarly, R is, it's 1 everywhere except when both of them are 0. In both those cases, you can see that the ones can be separated from zeros by a line. All I'm caring is, do you have a line? That's all. Yes, there's a line. In fact, an interesting question you can ask is, what's so great about this line? Why not this line? That's also a line. Okay. So one interesting question is, even when you actually have a line, you might differentiate between different kinds of lines. Did you see what I'm saying? So, for example, would you say this is a good line or this is a good line? If you have to, for this particular set of examples, you're looking for a line separating them. Which one, do you have any intuition as to which line you might prefer? Yes.
The one you control.
The one with the one in red, you mean?
The
dotted line. Yeah. So he's basically saying that he likes the dotted line more than the red line. Why? Well, it turns out that if you think of the gap, so it looks like all the zeros, basically you're looking at somehow the 0 guys are sort of in this region, and 1 guy seem to be in this region. You don't know. I mean, I just happen to tell you what the function is, so you know exactly where everything will be. If I just showed you examples, there are zeros this side, ones that side. I need to find a line to separate zeros from ones. It seems to be prudent to put the line that is equidistant from the closest zero and closest one. You guys get this? Do you see what I'm saying? Because if it turns out this thing wound up being a noisy example, and you're just basically coming too close to it, and so you're going to be a bad classifier. So to be a more robust classifier, you would like to do what's called max margin classifiers, which is the intuition that you guys just said. That is, if the positives are this side, negatives are this side, there's no point in saying, I'll come extremely close to the positives and say, that's the line. Might as well be somewhere in the middle, so that there will be more positives in between the positives and that I've seen and, and the line. And similarly, there can be more negatives in between the negatives I have seen and the line. This is called max margin classification. Yes.
But in this case, does that really matter if it can only take those two values?
No, the point is this sort of, the reason you had, the student had that intuition, I don't know which one, you're the one who said.
Yeah.
Why are you questioning your own intuition? Go with it.
I want to know why.
No, basically the reason is that you're worried that the original data might be noisy. You understand what I'm saying? Original data might be noisy. So I gave you a training data of criminals and non-criminals. What if some non-criminals I'm thinking are non-criminals are actually criminals who haven't been caught yet? And what if some of the criminals I gave you were wrongly convicted? Those are all bad labels. Training data is noisy. Teachers can be wrong, as much as it's hard to believe, right? So if the data is noisy, you are reducing your dependence on the data. So by the way, the reason I kind of went into this is this idea, this max margin classification led to something called support vector machines. For a while there, just like right now, for machine learning, you will say blah, 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 network. And then you'll say it's a good idea. For a while there, it will be blah, 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 machine. Like support vector, machine. Kernel, machine. Right? And this is support vector machine. And interestingly, this is no longer just minimizing error with respect to the, with respect to who has been classified right or wrong. It is also making sure that the classifying hyperplane is equidistant in some sense from the negatives and positives. The closest negative and the closest positive. That's a huge digression. Just so that you can say I've heard of support vector machines. Actually, I'm not teaching you the algorithm. I'm just telling you intuition as to what support vector machines do. Okay. Now, so here for R, I can do this. But for XR, which is the first bad case, you can't do a linear separator at all. Right? Because these are zeros and these are ones. There is no line that you can draw that separates zeros from ones. So Minsky and Papert wrote a book which basically says, nah, you can't even do XR. What the heck are you doing? DARPA should stop your funding. And then Frank Rosenblatt lost his funding. In fact, the second, third, fourth, 15th chapters of Minsky and Papert's book actually point out that multi-layer networks would work. But all that mattered was the first one said the current perceptrons don't work and that guy is getting too much funding. I mean, they didn't say that, but and that was enough to kill neural networks from 60s to 70s or maybe 75s. I don't particularly care about neural networks per se. I'm just saying how science progresses. There's no good reason as to why certain ideas will just stop being, how many of you heard of Katie Carrico? Katie Carrico. Anybody heard? She was the one who basically was working on the mRNA vaccines in UPenn. Nobody would give her any money. Nobody would give her any tenure. Nobody would give her anything. She finally retired and was just living a quiet life. At some point of time, actually, BioNTech started using the ideas, and after a whole bunch of time, and then Moderna started using. Moderna and BioNTech both gave her jobs. She started working with BioNTech. Now, because she lived this long, every possible prize in biology and medicine is going to her. She's going to also get Nobel Prize, probably. Right? So the point basically is that at the time they were giving up on certain ideas, there was no good reason as to why people gave up on mRNA at that time. Similarly, there's no good reason why perceptrons were given up between 70s and 80s. Okay, so by the way, it turns out that this is like the XR can actually be written as a network, except it won't be a two-layer net. It won't be a single layer network, it will be a two-layer network. Okay, which gets us to this point that if you want to do nonlinear decision surfaces, now this is the time that those of you who haven't seen that video should go back and see the playing with the TensorFlow sandbox. You can do basically two ways. One is first transform the data into higher dimensional space, find a linear surface there, come back to the previous space. That's basically what kernel machines do. The other is just learn directly nonlinear surfaces as multi-layer neural networks. The only worry is, can you train them efficiently enough? People were somehow worried that it can't be trained efficiently. They were not wrong. They cannot be trained all that efficiently. Except what changed is compute power has increased quite significantly. There are two things you need. One is data, the other is compute. And there used to be, I don't know, did I mention the Lena situation? Lena, the image processing lady. So for the whole entire area of image processing used to use this one picture of this lady called Lena. She was the Swedish model. Somebody somehow finally found a good scale, good scanner and scanned that, and that was the only picture that mostly people were using. It's that bad. People say, during depression, we used to get by with so little. Previous generations before cell phones, people used to get by with just Lena in image processing. Now everybody's cat and the cat's nephews are all on the internet. All pictures are all on the internet. And so there's huge number of examples. Plus there is compute. And so you could potentially do the training without worry. Okay. So that's what I was showing in this thing that you should definitely look at. One important thing I want to point out is to give this sense. I mean, for those of you who haven't seen this, to give this sense that if you have some inputs, x1, x2, you can make more new features, x1 square, x2 square, x1, x2 features. If you make these extra features, then you may actually be able to find a linear separating surface with respect to these new features. And a very nice telling example is this. This is as good a non-linearly separable situation as you can come up with. All the positives are inside the circle, all the negatives are outside the circle. Circle ain't no line. Right? How do we deal with this? Clearly, you can't apply a perceptron for this. But if you take these points, blow them up into a bigger dimensional space, where you have x1 square, x2 square here, x1, x2 here. In fact, this is a subspace. Imagine that if you are actually blowing them up, normally what you would have done is if you started having x1 square, x2 square, x1, x2, then you still will have x1 and x2 also as the dimensions. So you started with x1, x2. The superset is x1, x2, x1 square, x2 square, x1, x2. Even bigger superset is all of these and then the cubic terms. Even bigger superset is all of these and the fourth order terms. You see what I'm saying? But all of these can be computed from the input. All of these can be computed from the input. So there's no magic. If in this k-dimensional space, there may be a subspace where positives and negatives can be easily separated. So in particular, in the normal 5-dimensional space involving x1, x2, x1 square, x2 square, x1, x2, which is a 5-dimensional space, we'll have a 3-dimensional subspace. And in that 3-dimensional subspace, the one that I nicely picked, it turns out all the positives come this side, all the negatives come this side. There is a nice little plane that can be sitting. So if after you blew up the dimensions, you put in a perceptron, you're done. Because perceptron will find that line in that bigger dimensional space. Okay, so this is a very nice example to keep in mind. The only difference is here, and I think there was a question before we came to the class, that there's this here you are essentially deciding what are the new dimensions to compute like as of upfront. Okay, essentially these basically going for x power k kind of terms. That's basically what's called polynomial kernel. And so in some sense, you're trying to decide what sort of nonlinear terms of the inputs are you going to consider. In the example that I showed in the lecture that I recorded, I also consider other kinds of nonlinearities. For example, sine of x1, x2 is a nonlinear term in terms of x1, x2. Even sine of x1 is a nonlinear term in terms of x1. Those would be kind of not polynomial, but they are like just nonlinear terms derived from the original terms. You're trying if there is some random nonlinear combination of input features, which will basically have the separability. Going in the multi-layer neural network idea, what you would be doing essentially is you're in some sense, you're hoping to construct those features. It's not that you're doing it, but in effect, the interior nodes are computing some nonlinear combinations of the input nodes. And so if the whole thing is working, it must have been because these nonlinear combinations were the right ones that were able to separate. In the end, every network in the end will have a perceptron layer for a classifier. This is what I'm saying. It's a very useful thing to think about. So it's either input, perceptron is applied to classify. Either basically, normally perceptron might be applied with a softmax layer. That will still be a perceptron. Our input, whole bunch of translations, and perceptron is applied. The only question is who is doing the translation. The kernel case, you're just upfront deciding what additional terms are you going to put in. And then the last thing I want to mention is that is this basically that there are theorems essentially showing that really these two are identical ideas. That if for any arbitrary function in the universe, if it's a continuous function, there exists some two-layer network. That means a network with one hidden layer. The idea is every network will have input layer, output layer. In the perceptron, there's input, there's output. That's it. That's a one layer network. If you put any layer in between the inputs and the outputs, that means inputs are being converted into something in between, which are then fed to the output. That's called a hidden layer. It's hidden because it's not input, it's not output. If you have one hidden layer in the network, so of the many infinite number of one hidden layer networks, there exists some one hidden layer network that will be able to approximate any continuous function you can think of to arbitrary degree of accuracy. That's the great theorem about neural networks, about that. Now notice that's basically a variation of saying, so when I said that essentially the one hidden layer, I didn't tell you how wide that hidden layer is going to be. It actually can be infinitely wide. If you consider infinitely wide networks, you could potentially have started from input, did a polynomial kernel, that means you have all possible polynomial terms, infinite number of polynomial terms, and then you threw in a perceptron layer outside. It looks like a multi-layer network with one hidden layer. They're both equally expressive. So in fact, there are theorems showing that clearly kernel machines and perceptrons are of equal expressiveness. The only other thing is if you have two hidden layers, then even a discontinuous function can be approximated. Notice that these are just mathematical theorems showing that it will be possible if you, at least it is there in the search space. You will be able to find a network in the search space, assuming everything else goes right, assuming you have like an optimization, like a gradient descent that doesn't get stuck in local minima, etc. If it isn't even there, you can't find it. If it is there, you may still not find it. This one is just saying it is going to be there. But what do we actually look for that? No, what mostly people do is they will just pick some network of some number of layers. Okay, and then essentially try to, so you network, no, we'll stop it here, but this was just a one hidden layer network. It has more weights. Input is connected to the middle layer is connected to the output. You can think of them, the simplest case is fully connected or dense networks. Where everything is connected to everything in the next layer. There's nothing wrong with it because the weights can be zero. And if the weights are zero, it's as if the connection doesn't exist. So you put all the connections, and if they become zero, you're fine. And who makes them zero? The gradient descent is supposed to make them zero. And the question, of course, is how do you change the weights? That was what I was telling you, that essentially we'll come back to the next class, but essentially it's the same differentials, same weight differentials with respect to the error are used. Okay, and just before you go off to the false break, I'll say that thankfully you don't have to deal with this. I'll tell you about this. Here you would put a function such as that function as a graph. And so you can essentially compute the output by just going through the graph, unit by unit. And the backpropagation on that just goes step by step by step. I'll explain to you how individual steps are done. Once you do that, you have a little program, and that program can essentially take any arbitrary function. One of the greatest things about programs is you can stack programs with infinite depth. That's what is auto differentiation. So we will be fine once you come back. Have a good break.